Perfect. Okay, now, finally. Hey, a very warm welcome from my side. I do apologize for these technical difficulties. That's what you get when you don't test the microphone. Well, I hope you had a great time so far at the conference. My name is Daniel Marbach. I'm from Switzerland. And should you have any questions that I cannot answer during this talk, you find my X details and my email address and my LinkedIn details on the slides. I will also share it again towards the end of the talk. So I have a quick question to the audience here. Who is new to benchmarking? The audience, hands up. Quite a few. Who is new to performance profiling? Okay, who is new to benchmarking and performance profiling? Quite a few. Okay, then this is perfect. Because I remember sort of the first time when I started benchmarking my code to sort of verify whether my changes that I sort of envisioned are actually making things faster, accelerating my code, or whether they're actually making things worse, right? Because we want to measure to see. And I've already seen quite a few benchmarks like the one on the screen here written in benchmark.net. And don't bother too much about the code on the slide because that's not really the intent that I'm showing here. I'm just showing you an example of a benchmark because I also didn't really think about it much either because I wrote those blog posts and I was like, yeah, you know, it's a class with a bunch of attributes. I've already seen and written quite a few unit tests with things like XUnit, NUnit, or God forbid MS Test. I had to use it for some time to time, and I didn't like it. But I know it has been improving over time. But yeah, I felt quite certain when I was trying to write my first benchmark for my production code that it's just going to be as simple as a unit test, right? So just slap a bunch of attributes on a class, and everything will be golden, right? But I was wrong. I mean, writing the skeleton of the benchmark was actually indeed very simple because it's a class with a bunch of attributes. But then the mind-boggling part was I was trying to sort of figure out what should actually be taken into account in the benchmark. And then I was also thinking, well, how do you isolate my production code that is probably quite messy because I wrote it? Right? How do I isolate it and then sort of make sure I can measure things without investing crazy amount of refactoring sort of into the code so that I can actually put it into a benchmark? And then I was also thinking, what should I actually take into account or what should I deliberately cut away from my code because it would just skew my results for the things that I was trying to see? And then I was also thinking, well, but how do I go through this cycle of sort of going through measure, change, and measure without burning away my allotted budget that I had for these performance optimizations, right? Because at the end of the day, my task as a senior software engineer, a solution architect, whatever you are or I am, right, is I call myself principal chocolate lover because I got so fed up with job titles these days. But anyway, so my job is to write business code, is to write framework and libraries that make my customers successful. My job is not, I'm not titled as a performance engineer or anything like that, right? So I have to carefully balance the time that I have available between shipping features that make an impact on the customers versus doing some types of performance optimizations. And sometimes the performance optimizations that I'm making, I'm doing that as sort of a fun project in the evenings, sitting in front of the TV to just improve things a little bit and sort of feed my inner curiosity to sort of improve the code, right? But then the question is also, why would you even go through this hassle to even do these optimizations, right? So for code that is executed at scale, the overall throughput and memory characteristics are really important because essentially code that wastes unnecessary CPU cycles and memory is going to eat away resources and therefore energy in your data centers, whether it's on premises or in the cloud, right? So we want to make sure that we use the energy that we have available as efficiently as possible to also reduce the carbon footprint these days, right? Because we heard all about green IT movement and stuff like that. We have scarce resources on planet Earth, so we want to make sure that we use those things efficiently. But even if you remove sort of the green IT aspect, right, and you're saying, well, we're running in the cloud. Well, we have a credit card or whatever associated with a subscription, right? And these days, we have sort of these virtual sort of money things that is called, it's some arbitrary number, whether it's premium units, messaging units, or I don't know, gigabyte per second, whatever, that sort of, when we use resources in the cloud, at the end of the day, we're going to get billed on the credit card, right? So that means the more efficient the code is, the more we can actually execute and the more requests we can serve for the same amount of money, right? So that means we have to take care of that our code is also efficient in the cloud. But let me give you a more concrete example of a quote from Microsoft. So Microsoft has this blog post series where they sort of talk about sort of the migration scenarios of their internal teams. And this is one example of the migration story from the Microsoft Teams infrastructure and Azure Communication Service team. And they migrated from .NET Framework to .NET 6. And they sort of managed to have we're able to see Azure compute cost reduction of up to 50% per month. On average, we observed 24% monthly cost reduction after migrating to .NET 6. The reduction in cores reduced Azure spend by 24%. And the performance improvement were 30 to 50% improvements in performance, including P99 CPU utilization and P99 service latency, right? Just by migrating, and I'm saying just, I know this is a very simple word, just by migrating essentially from .NET Framework to .NET 6 and leveraging more modern programming techniques to opt into the performance improvement that .NET 6 provides, they were able to reduce their Azure compute spend by 24%. And that's amazing, right, if you factor that in. I'm pretty sure if you go to your boss and tell your boss, I was able to reduce our Azure spend by 10%, your boss is also already amazingly happy. But if you say like 24%, you will get a bonus. I can assure you. But in this talk, I have summarized sort of my personal lessons on how to sort of make performance optimizations actionable. Because I like to have a practical approach that you can also use in order to sort of improve things, identify bottlenecks, and then from there, over a cycles of measure, change, and measure, actually improving your code as well. But to start on this journey, you have to become performance aware. And for me, one of the key principles that I always apply to almost everything that I do in software is I try to make explicit trade-offs in the decisions that I'm making, right? So this also applies for me to performance. And the reasonable, mature team should be performance aware. So, like my friend Martin Bouw from Belgium, he's also here at the JetBrains booth, once famously said, in some countries, you have to be bear aware for the likelihood, when you're hiking, for the likelihood of a bear to cross your path, right? So, but actually, that's probably the case in Canada. It's probably not the case in Switzerland, but actually I did some research in preparation for this talk. Apparently, bears disappeared in Switzerland for almost 100 years. But in sort of 2005, and one single brown bear started crossing from north of Italy over the South Switzerland border, and there is a likelihood that a bear will cross your path. So as long as you know how to react when a bear crosses your path, and you apply all those principles in the situations where you need it, then you're fine. But I'm totally digressing here. But my point is, you should be doing the same for your performance, right? Build up a performance awareness, and then you know what to do in order to make the explicit trade-offs in your projects as well. But when it comes to performance, and when you're performance aware, it doesn't mean you have to go always all in. On the contrary, in fact, I always start with the simplest solution first. So I take the business requirements, I think about what is the simplest way to implement this thing, right? I do not care about performance, I just make sure I have reasonable test coverage in place, I implement the feature, I look at the code, and it passes the tests, and that's probably a point in time I could ship it. Or I can sort of make a step back and ask myself a bunch of questions. And these questions that I usually ask myself here are the following. How is this code going to be executed at scale? And what would be the memory characteristics of this code be? This is just the gut feeling based on my over 15 years of being a .NET senior software backend engineer, right? So I ask myself that question, and then I start looking at the code. What can I change? And then I ask myself, are there simple low-hanging fruits that I can apply here? Because I already have a code that works and I have test coverage, right? So I can start making some changes without breaking stuff. Then I sort of ask myself the question, are there things I can move away from the hot path by simply restructuring my code a little bit, right? Because anything you do on the hot path that is costly, that you can move away from the hot path, like allocating a byte array and reusing the byte array, that's amazing because then you're not allocating a byte array anymore on the hot path. Then the question I also ask myself, what part is under my control and what isn't, right? Because sometimes performance optimizations require to talk to another team. Maybe they have their own agenda, their pressure, right? So I cannot influence them. Or maybe I'm using a third-party library. Maybe it's open source and I'm lucky and I can spend the time to improve the open source library. Maybe it's closed source, right? Then I have to talk to a third-party vendor, convince them with whatever I have that there is a problem in their library. So I have to make these trade-offs as well. Because again, I have to be cognizant about the time investment. And then the question is also, what optimizations can I apply and when should I stop? Right? This is a very important question because I told you I'm not a performance engineer and it's important for me to deliver business value to my customers, right? So I need to make these trade-offs. And especially, I can wholeheartedly say performance optimizations can be quite addictive, right? And I want to be cognizant in that mode of feeding my sort of inner geek and doing performance optimizations versus, am I still on the right track? Is the sort of the effort to value ratio still good, right? We have to keep that in mind. So it's all about finding the right balance. If you want to know more about the trade-offs, I gave a talk also at NDC called Performance Tricks I Learned from Contributing to Open Source .NET Packages. It's available on this QR code. You can scan it and you can watch it. Should you be interested to go more in depth into what concrete things can you do in .NET and C# to optimize and make your code more performant? This is not the focus of today's talk. By the way, if you don't manage to make a picture, I also share a link to a repository towards the end of the talk with all the resources. Good. But then once I sort of start into the process, so I ask myself, what am I actually doing when I'm doing performance optimizations? And I came up with what I would say a great mechanical approach that you can also use to do performance optimizations. I call it the performance loop. And the performance loop, it starts very simple. So first of all, what I'm doing is I'm writing a sample or a performance harness that makes it possible to observe the thing that I want to see under a profiler. And usually what I do, which is very important, I take at least a memory profile and a CPU profile. If you have code that is also doing I/O-bound stuff like database operations, HTTP client calls, you also want to take an I/O profile. But the I/O profiling is not part of my talk today. I'm only going, in the interest of time, going to show you memory and CPU profiling. But I want to make sure that you keep in mind that I/O-bound stuff is always hundreds, sometimes thousands of times slower than CPU and memory stuff, right? So you might want to look into that stuff as well. But again, that's not the focus of the talk. Because what that test harness gives me with those two profiling sessions, it gives me an overview of all the subsystems at play, and they can actually make explicit trade-offs where to focus on, right? Good. And then the next thing that I start doing is I select the hot path. For example, the one that is responsible for the majority of allocations or for the biggest CPU slowdown, or whether I feel I can make a good enough impact on this code here. And that impact can sometimes be, maybe I see some allocations, but I don't have the expertise, the knowledge to figure out something over there. So I focus on the parts that I know I have knowledge in, because knowledge is crucial to actually make these performance optimizations. And I tend to not think too much about, oh, there is like 100 megabytes of allocation over there and only 20 over there, but that's where my knowledge is. Because at the end of the day, what I care about is I sort of apply the principle of 1% improvements over time. right? Because the .NET team, by the way, does exactly the same thing. Because the idea is when you're making 1% improvement over the entire code base in several iterations over several major versions like the .NET framework, the compounding effect of these 1% improvements will make a huge impact anyway. So don't focus too much on like, oh, there is this huge allocation over there. And then when I do improvements, I also add more test coverage in place, because at the end of the day, right, it's basically useless if you have optimized the code, but the code is broken, right? It doesn't help when the code is utterly fast but doesn't work, right? So I want to make sure that things are actually good. And then the next thing that I'm doing is I start sort of benchmarking. What I usually do is, to save some time, I extract the code into a dedicated repository as well as possible, and then I do a series of short runs to essentially see whether I'm heading in the right direction. I'm going to talk more about short runs, what they are. And once I'm reasonably happy with the outcome, I do a full chop run, which gives me statistical results that I actually care about, that give me sort of a good indication where I am. And then, once I'm done there, I sometimes go in cycles, what I call the inner loop of this performance loop, right? Because sometimes I improve, I benchmark, and I see, oh, it's actually going in the right direction. But now I have more ideas, so I improve it again, benchmark it again, and then I see, oh, I'm going now in the wrong direction. Maybe let's go back, right? So I do this sort of in iterations. And then, what is usually forgotten by many people, at the end, when I'm done, when I'm reasonably certain this is actually doing well, I put it back into the sample or performance harness that I wrote before to actually make sure that in the grand scheme of things, the changes that I made are actually improving the memory profile and the CPU profile, right? And then I ship the code and focus on other things in my code base. Shipping the code that you just optimized, it sounds so obvious, but it's really important, because if it's just sitting somewhere on a branch and it's not in production, sorry, you don't know whether your changes actually are making an impact, right? Because sometimes the assumptions that we're making in our code, when we're optimizing and writing the code, they turn out to not be true in production, right? So go back, put it in production, put on your monitoring system and see what actually is going on. But let's see how we can apply this sort of performance loop to a more practical example. Because I work at particular software and I'm a framework and library engineer, I'm going to show you an example out of my profession as in a framework and library, but I'm 100% certain whatever I'm showing you today with this framework of library applies also to your business code. So please bear with me a little bit. So NServiceBus is basically a messaging library that sort of feeds messages from queuing system like Azure Service Bus, SQS, SNS, MSMQ on premises, SQL Server, Postgres server, and whatnot. And what it does, it sort of tries to sort of execute our customer's code. And that is sort of the message pump that I have visualized there. And if you want to know more about what NServiceBus does, because I cannot cover this and it's not the focus of this talk, you can go to go.particular.net/ndc-oslo-2024-quickstart. But let's have a look at how NServiceBus works internally. So NServiceBus has the most critical infrastructure piece inside NServiceBus is called the NServiceBus pipeline. So the NServiceBus pipeline is sort of the engine that drives all the stuff that is plugged into NServiceBus. And NServiceBus has in the pipeline a series of behaviors, and those behaviors sort of NServiceBus follows the open-close principle. And what we can do is there is a core thing which is called the pipeline, and there can be extensions that are plugged into that pipeline that do a bunch of stuff. Like, for example, it does transaction management, it does unit of work management, it does serialization, deserialization, routing against multiple queuing system, and all that type of stuff, or calling into DynamoDB, Cosmos DB, SQL Server, Entity Framework, and Hibernate, right? So there's lots of things going on in that pipeline. And as such, because it invokes at the end of the day our customer's code, we want to make sure this pipeline is as efficiently as possible. if you're not familiar with behaviors, you can conceptualize behaviors similar to ASP.NET Core middleware, right? So ASP.NET Core, they have this middleware thing where you can basically have a method that is called invoke, or you can use the minimal API approach where you get a next delegate into your code, and then you can essentially execute code before the next delegate and after the next delegate. So you can actually wrap the entire ASP.NET Core pipeline with a try-catch as an example, or with a transaction, whatever you want to do. And behaviors are pretty similar in NServiceBus, right? So we essentially inherit from behavior, we define some state, and then we have a next, and we can execute basically code before and after, and we can wrap things in a try-catch, right? And that's where we actually do our deserialization, serialization, database transaction management and whatnot, and where our customers also plug in stuff into the pipeline to sort of follow the open-close principle there, right? And I told you, I'm showing you this example with NServiceBus, which is a framework and library, and you might be thinking, yeah, but Daniel, come on, you're a framework and library developer. Why are you telling me all this? This is not applicable to my business code. All what I'm showing you today with examples of NServiceBus applies one-to-one for your business code as well. So if you stick to the practical approach that I'm showing you here with this concrete example, you will be successful as well in your stuff. Okay, let's look into profiling the pipeline. So we are now entering the first step of the performance loop, right? So to get an overview of the problem domain, in front of me, I'm creating sort of this sample or profiling harness that sort of tests the thing that I want to see under a specific subset, specifically for what I'm going to investigate into, right? So what I'm essentially doing is, for example, because I want to test the pipeline invocation speed and the pipeline throughput, I'm setting up a sort of a profiling harness that sort of makes sure I can see the relevant pipeline stuff under that harness. And then I told you already before, but I'm going to repeat it because it's so important. What I'm doing is I'm taking a CPU profile and I'm taking a memory profile. I usually use the JetBrains tools like .memory and .trace because I'm a big fan of those. But don't get me wrong, your mileage may vary, right? Depending on your subscription level with Visual Studio, you can apply the same thing that I'm showing you today with the JetBrains tool with Visual Studio, right? Or if you're saying, well, I don't have I don't have commercial tools available. Can't you show me something, a free tool? There is, for example, if you're running on Windows, there is Purview. You can freely download, you can use Purview. Although I would say Purview is a very advanced tool. Every time I open it, I need to download the cheat sheet again to remember all the very advanced commands to actually go through Purview. But I'm showing you it today with the JetBrains tools, but you can apply exactly the same thing with any other tools, whatever you like, right? And as a matter of fact, sometimes, depending on the complexity of the performance investigation, I even use multiple tools to sort of, I know it when I see it kind of principle, right? So I need to have multiple views on my code. Good, let's have a look how a harness looks like. So first of all, I'm setting up NServiceBus with a transport and a serializer and something of my choice. So this is my harness. So what I'm doing is I'm making trade-offs. So for example, I was running on Windows, so I use the MSMQ transport because it's available. I know it's very old school, but it works. I don't have to install anything. It just works. It's there on my machine. Then what I do is I sort of configure a reasonably fast serializer. So I'm using the system text JSON serializer. That's what I'm doing. And then the next thing is, because I care about sort of measuring the raw execution speed of the pipeline, and I'm not interested in IO-bound stuff, I configure NServiceBus using the in-memory persistence, right? Because I don't want to use Cosmos DB or SQL Server or whatever, right? Because that's not the focus of my performance investigation. Then I have a bunch of console write lines and read lines in that harness that sort of tell me, now is the stuff over that you don't want to see, you can now attach the profiler, right? Take a snapshot. That's what I'm doing here. And then what I'm doing is, because I want to sort of test the pipeline, I know that when I do endpoint instance.publish, the publish pipeline is going to be executed, right? So I sort of publish 1,000 messages concurrently with NServiceBus.
then the next thing that I'm doing is I know there is not just the publish pipeline based on my domain knowledge, there is also the receive pipeline, because when I send messages, they will come in again at some point, right? I will receive messages. So what I do is I add a handler that sort of receives those messages, and then what's going to happen is whenever a handler is invoked, right, I concurrently published 1,000 messages, and now 1,000 messages come over in on the other side and will execute this piece of code, and that's where the receive pipeline will be executed, right? So now I have all the things in place that I need to sort of observe things. And this is the test harness, how it looks like. But you might be asking yourself, but I mean, yes, you showed me now this concrete example with NServiceBus, but what else do I need to take into account for my test harnesses? I have a bunch of principles that I want to give you away. So the first one is pretty obvious. You're like, Daniel, come on, seriously? I mean, you have to compile it and execute it in release mode. Well, yes, it's super obvious, but I can tell you, usually the default settings in your IDs is always the debug state, right? The amount of times I personally have forgotten to switch it to release mode, it's actually staggering. Then it has to run a few seconds because we want to take sort of a profiler snapshot, so it has to run a few seconds. It can't be just a few milliseconds because then we probably won't see anything. And it should keep the overhead of all the things that we don't want to see pretty minimal. And then usually it's also good practice, depending on what you're trying to measure, to sort of disable the tier chit compilation. And then, in order to see the full stack trace, also add debug type to PDB only and add the debug symbols. Because when you have that, you will see the full stack trace essentially in your profiling snapshots. Okay, now that we have that in the harness, we can actually see what's going on. And I'm going to show you now a few concrete screenshots of this example. So I filter in on the sort of publish operation because I want to look at the sort of publish pipeline. And then what I see here is that I'm exploring the memory allocations. And you might be asking yourself, but Daniel, why memory and not CPU first, right? See, isn't CPU way more important? Well, the thing is, what I've learned based on my experience and also from, for example, David Fowler recently tweeted that one of the biggest sources of allocations and slowdowns in .NET applications still up to today is, for example, memory stream to array or byte array allocations. And usually what you can do is you can get a lot of bang for the buck when you optimize away memory allocations. That's why I'm focusing on this part first. Because once we go into sort of CPU algorithmic complexity and stuff like that, things are getting very, very complicated. And we can sort of get a lot of small wins by actually focusing on memory allocations. And what I see here on this screenshot is a bunch of byte array, stream writer, message queue permission, memory stream set capacity allocations, and jar array allocations, and whatnot. They are super hefty, right? And now again, you say, well, let's get rid of those. But no, because I'm focusing on the pipeline with my domain knowledge. I'm basically focusing, it's like, this is what I care about. So I see here, I have 20 megabytes of memory allocations from a thing called behavior chain invoke. And that's where the publish pipeline is invoked. But then I also have to look at the receive part, right? Because I want to get a full overview of what's actually going on. So then what I do is I sort of zoom in the receive part. And again, I have lots of byte array, XML text reader nodes, and message extension allocations. But again, I'm zooming in, and I'm sort of knowing that here I have 27.83 megabytes of allocations that are coming from the pipeline, right? And then again, you might be asking yourself, but Daniel, come on, like seriously? You have like 200 megabytes of byte array and message extension allocations, and you're focusing on 20 megabyte or 27 megabyte of allocations. You're nuts, right? Why are you doing that to yourself? Well, again, I think ideally, of course, you would like to get rid of all the allocations, right, in our code base, because then the code is utterly fast, right? But usually, the context that you have, the knowledge that you have, or I have in the specific example, is really crucial to guide you through sort of that noise that you see in those profiler sort of snapshots, right? Because I can tell you, I used MSMQ, right? And what's there, most of the allocations that you saw on the screenshot, they came from the MSMQ transport. And MSMQ transport is sort of a legacy thing that most of our customers are transitioning away of. They're moving to RabbitMQ, Azure Service Bus, SQS, SNS, right? So if I invest time into optimizing MSMQ, then I'm basically not doing all the other customers a favor, and I'm optimizing for a diminishing user base. So that's not a good investment of my time, right? And another angle can also be, I might not be an MSMQ expert, so I would have to first ramp up my knowledge to actually understand what's going on there, to actually make a meaningful impact, right? Or the code is in a Microsoft code base that will never be touched again because MSMQ is done, right? So why would I focus my efforts there? And then again, I told you already this 1% improvements, right? By making iterative gains on the hot path, I will get overall improvements across the code base anyway, so I don't have to focus on these allocations. And again, the pipeline optimizations that I'm doing, they benefit all the users, regardless of the transport they're running on, so I want to focus on that, right? So what I'm telling you here is the context that you have about your code base is crucial to guide you through what you're doing in the performance optimizations, right? And make those trade-offs explicitly with your team colleagues, and even better, write them down when you're making them, right? Do a decision log, design decision log, or let's say performance investigation decision log to write it down so that it's captured, so that you know it the next time and you can share it with others. And maybe if you're a senior developer, you can also teach your newer developers to do these types of performance optimizations. So let's have another look at when we zoom in into sort of more of the pipeline, we can see that there is a bunch of function, task, behavior, display class allocations that are also sort of related to the pipeline. And then with, for example, a tool like .memory, you can also filter by namespace. And Visual Studio can do that as well. Purview can do that as well. So you sort of filter into the NServiceBus pipeline namespace, or whatever namespace you're looking at when you do this performance optimization. And then I can see all the allocations that are coming from there. So now we have a good overview of the memory characteristics. So let's look now at the CPU characteristics, right? So sometimes code spends a lot of time in doing algorithmic stuff, right? And we want to make sure that this is efficient, because when we're burning away CPU, that can significantly slow down things on the hot path. And one good thing that you can do is you can leverage flame graphs to actually see what's going on. Flame graphs are really, really helpful to get a good overview of the performance characteristics. And I'm going to show you here this flame graph. I know this is probably very tiny for you, but I'm going to quickly walk you through it. So the flame graph here on the screen, you sort of read it from top to bottom. And the top entry point is sort of the publish pipeline. And one of the good things about flame graphs, even if you don't even know what's on the screen, what you can see is there are bars, right? And those bars, they have a length. And what's the good thing about the flame graph is basically the top one represents sort of the length or the execution time of sort of the entire code that is underneath there. So that means essentially the length of the topmost sort of bar is sort of, it's the own execution time of that function plus the execution time of all the thing that is underneath, right? So the good thing is that without having a really good understanding of sort of how many milliseconds or whatever it is, I can look at the flame graph and I can see, oh, there is a bunch of red stuff, right, that is pretty hefty, and there is a bunch of orange stuff. And the bunch of red stuff, what that means for me, I know this is infrastructure code that executes the pipeline. The orange stuff is actually the actual business code that gets executed. And I can already say it just by sort of looking at this flame graph, oh, there is something off, right? The relationship between the red part and the orange part is way off. So there is probably a lot of room for improvements here. And we can just by looking at the flame graph, right? And when we zoom that in, we see that even better, right? So we essentially see is we have this mutate outgoing message behavior invoked. That's the actual business code that is executed. And then we have gibberish, and then we have apply reply to address behavior, which is the other sort of business code, right? So in between the business code, we have a bunch of infrastructure noise that we might be able to get rid of it. But if you're saying, well, flame graphs, okay, I get it, but it looks very complicated on the screen. Most of the tools, they also have sort of a CPU overview that you can use to filter in. So for example, .trace has the hotspots overview, and I did filter in there for the publish operation, and then you see in percentage how much CPU has been spent. So when we zoom in, we can see on the publish pipeline, we have sort of 20% is spent there, and 12.3% is sort of spent in the behavior chain invocation. So as a total, 32.3% of the CPU is spent in executing the mechanics of the pipeline, right? What we have seen already before on the flame graph with sort of the relationship between the red and the orange part is also clearly visible here in numbers, in percentages on the hotspot overview. Good. Then let's have a look at the receive part. It's slightly less dramatic, but again, if we filter in on sort of the receive part, when the messages are coming in, we can see that sort of the behavior chain is consuming 4.8% and 9.2%. So in total, if I can do the math this morning, 14%. So a seventh of the overall CPU time when sort of receiving a message is essentially spent in infrastructure stuff that is not really necessary. But now we are ready to sort of make changes to the code base and start improving things, right? Because now we know what's going on. We have a good understanding. But hold on your horses, right? I told you, before we sort of improve, we essentially want to make sure that we have some good test coverage in place, right? And usually what I do is I think about, because by looking at the code, by doing these performance investigations, I already build up context and knowledge that helps me to make sort of design decision trade-offs. And then I have a bunch of ideas, and then I'll look at the test and say, do the test actually make sure that when I start introducing these ideas that I'm not breaking stuff, right? And here, I already had a few acceptance tests in place, but I knew that I'm going to do some fancy stuff with expression tree compiling and whatever, probably, right? And that might lead to some code that might statically cache stuff, and that's dangerous. So I introduced tests that make sure that I'm never actually caching state that should never be cached. So I introduced those sort of safety nets so that I can freely make these optimizations, right? Good. Then, if you want to know more about the concrete things that I did, I have a few blog posts. I wrote a few blog posts, and one is called 10 times faster execution with compiled expression trees, or how we achieve 5x faster pipeline execution by removing closure allocations. You find those on go.particular.net/NDC-Oslo-2024-pipeline, but this is not sort of the topic of this talk. I know these are very clickbaity titles, but I think we actually made 10x improvement and 5x improvements. They're not just clickbaity. So if you're interested to see more concrete things, how I did these performance optimizations, go read those blog posts. Good. But now, let's have a look at how we can actually benchmark the pipeline, right? Usually, when we look at actual production code, right, compared to all the blog posts we have seen about benchmark.net, you always see people are just testing one method, right? And they're, yeah, that's easy. But our code is never usually just one static method that just does a single thing, right? Usually, essentially, when we look at the code that we have out there, software is way messier than we like to admit, right? Or especially the code that I have written, usually. Have you ever had that, by the way? You're sort of opening some code and you look at it, it's like, what the hell is going on here? And then you do a git blame and you realize it was you 3 months before. That happens to me all the time. So, but yeah, or as Gordon Ramsay would say, right, software is a disgusting, festering mess. But essentially, what's important, right? Usually when we have software or code in our production code, it's not a single method. It's a bunch of components that sort of are intertwined with each other, right? And we need to sort of make sure that we only are sort of taking things into account that are really sort of important for the things that we are trying to sort of measure, right? So what I usually do is I came up with a very pragmatic approach. So what I do is I essentially copy-paste the source code of the things that I do, and I put it into a dedicated repository. So I basically freeze the code as it is, copy-paste it over, and then I have a playground that can start playing around. And so I take all the code, and then what I do is I adjust the code that I have to the bare essentials to create a controllable environment that allows me to measure the things that I want to see. I know this sounds like, well, but Daniel, come on, now you're copy-pasting code, but the code will evolve, right? And how do you make sure that things are not regressing? I'm going to quickly talk about regression testing as well a little bit later, but this is more or less the approach that I usually use to get started with, and I was very successful with this approach. So I have here a concrete example. So I took everything that is related to the pipeline execution engine, which you can see is a bunch of interfaces, classes, and components that interact with each other, right? This is non-trivial code. And I put it into this repository, and then I started faking away things that I'm not interested in. So what I did in this concrete example was I basically trimmed down everything to the relevant behavior. So I ripped out all the stuff in there that is not relevant for my benchmark. Then I replaced the dependency injection container that was in place. I ripped it out, and I sort of just newed up classes. Because I don't want to benchmark, I don't know, the Microsoft dependency injection abstraction or structure map or artifact. This is not my goal. I want to benchmark the raw pipeline execution speed. So I have to remove this noise. Then I also replaced all the IO-bound operations with a task completed task. Because again, I'm interested in sort of the actual raw execution speed and not the IO-bound operations. And you might be saying, for those that are a bit more advanced with async await, but Daniel, I know you're cheating here because you're not actually yielding the thread back to the worker thread pool and whatever. This is clearly not a reliable benchmark. It's like, well, you're kind of right, but you're also not. Right? It really depends on the scenario. Here, I'm not interested in sort of the concurrent execution. I'm only interested in the raw execution speed of a pipeline invocation. And therefore, it's totally okay to sort of return task completed. Plus, with benchmark.net, that I'm going to show you a little bit later, it actually does statistical analysis, and sort of that yielding would essentially, in the statistical result, would sort of blend in. So it doesn't matter for the scenario that I'm doing here. Good. And I told you it's potentially a little bit controversial, right? Because I'm copy-pasting code. But I want to give you a good approach that you can get started with sort of as a 80-20% rule, right? For code that is not changing that often, this approach of copy-pasting code works really, really well, right? Because you can freeze it in your environment. You can make a bunch of contextual decisions to actually tweak it to your needs, and then you have an execution environment that doesn't move away, and you don't influence things with your other teammates, right? Because what I want to sort of give you away is this gives you a good step-by-step approach to get started building up this performance culture. Because being performance aware, it sounds so easy in a talk at NDC, right? But this is going to take you months, potentially years as an organization to sort of build up, right? So you want to make sure that you can get started with, and that you can teach your colleagues to essentially be successful with these types of investigations before you go into like building an entire performance-aware culture. Because once you go into doing more regression testing or CI/CD stuff, right, you have to ask yourself a bunch of questions like, how do I reliably run those tests, right? How do I set up the CI/CD to actually execute this benchmark? Can I even execute those on the CI/CD system? Should I have dedicated hardware available to execute this test to actually have reliable results? And all those types of questions, you don't have to ask yourself those questions at the beginning of your journey, right? That's why I want to make sure you get started with a gradual approach. And then I told you I had this very sort of basic understanding at the beginning. I sort of said, well, a benchmark is like a unit test, right? because I can just slap a bunch of attributes to it and then something gets executed. But this is actually a completely wrong understanding of a benchmark, because when we write a unit test, what we do, ideally, we want to test all the methods and all the properties and all the edge cases, right? Because we want to make sure that under edge cases, the stuff that we have in place also works. And at the end of the day, what the result is of a unit test, it's either sort of passed or failed, right? It's green or it's red. But the benchmark is completely different, because when we execute the benchmark, what we are sort of getting is we are doing many thousands of iterations until we have a statistically significant stable result. So the result of a benchmark is not green or red, it's actually a bunch of numbers, right? Like mean, standard deviation, error, and whatnot, like I'm presenting here on the screen, plus all the parameters, the permutations of this benchmark. So what that means is essentially we have to execute it until the results are stable, because we want to make sure that we have outliers removed and whatnot. So we are going to execute this hundreds and thousands of times in iterations. So that means a benchmark by nature takes minutes up to hours, depending on the use case scenarios that you're testing, right? So that's why we have to make the trade-offs and actually say, well, let's just test the most common cases that are frequently used on the hot path, right? With the amount of required permutations. Because if we're going all in, like with a unit test, this is going to take ages, and we will never get the results, and they're complex to maintain, whatever. So we need to make this sort of trade-offs. And then, again, what is also important, I talked about permutations, so input parameters that sort of define the permutations for the benchmark. Here, we should derive them from production usage scenarios, right? Because we want to have a realistic enough benchmark that gives us an indication of what's going on with production scenarios, right? So that's what a benchmark is. So get rid of that sort of conceptual understanding. It's like a unit test because it looks similar with a bunch of attributes. It's not, right? Good. Let me give you a concrete example of how this looks like with benchmark.net with the pipeline execution. So the first scenario is, obviously, I want to test the raw pipeline execution speed. So what I do here is I have the global setup attribute. And in there, by the way, you don't have to fully understand this code. This is not really the point. I know it's a lot. But essentially here, what I'm doing is I'm setting up the pipeline. And what I'm doing is I'm sort of initializing the pipeline, and I'm doing this in a global setup to make sure, because I'm not interested in how long does it take to set up the pipeline. That's not the scenario. I want to see how long does it take to execute the pipeline, right? So the setup is in a global setup, so that will not be measured by benchmark.net. And then what I think about is, okay, what are potential permutations? So here, what I thought about is like, okay, we have a deepness of the pipeline. And I looked at the usage scenarios of how we extend the pipeline, our customer cases that we have in Salesforce, our documentation and samples. How many things do usually people plug into the pipeline, right? And then I came up with a deepness of 10, 20, and 40, which is a more or less accurate representation of what people have in their production scenarios, right? So that's how I sort of permutate the pipeline execution and sort of build up the pipeline deepness here. And then what I do is I add this short run attribute on the top. What that means is, to benchmark.net, just do a quick run. Don't go into like all statistical analysis, and it's going to take minutes, multiple minutes. Just do a quick run to give me a sort of an indication, am I heading in the right direction, right? Because I'm still sort of in the improve benchmark type of inner loop here. And then I add the memory diagnoser, because I am also interested to see all the memory allocations, okay? And then what I do is I have the baseline benchmark, which executes the benchmark before, the pipeline before my changes, and then I have the other one that executes the pipeline after my change, so that I can compare the two things. Good. So that is the pipeline execution. And then you might be asking yourself, well, but Daniel, you show me this concrete example. What are actually good practices I can take away from this talk for my own benchmarks? What should I care about when I write my own benchmarks? So I have a few. So a benchmark should be following the single responsibility principles, like any other methods in your code base. So basically, a benchmark should basically measure a single thing. So here I did pipeline execution with permutations for the pipeline execution. That's a single scenario. Then a benchmark should have no side effects, right? So because any sort of state that you accumulate over the benchmark iterations influences all the other iterations, and that is a side effect that you don't want to have. We need to sort of avoid that. Then the other thing is it should sort of prevent dead code elimination. Because usually when you're not using the things that you're sort of instantiating in your benchmark, what's going to happen is the JIT, the just-in-time compiler, looks at your code and says, oh, this local variable is not going to be used, so it optimizes it away. And then you're measuring nothing. Right? So with benchmark.net, what you can do is you can return the stuff that you allocated back over the method, or there's a consumer class that you can use to consume whatever you're allocating to make sure the JIT doesn't remove away this code. And then I highly recommend you to delegate all the heavy lifting of doing the benchmarks to a framework like benchmark.net, because benchmarking is pretty hard and you don't want to do that yourself. And then be as explicit as you can. So when you write the benchmark, the code should basically have no implicit casting and stuff like that, or use explicit types wherever possible to sort of make sure that when you look at the benchmark, all the potential side effects that can occur are clearly visible in this code, right? Because otherwise the complexity is too high. And then this might sound very obvious, but it's very tempting from time to time when you're sort of in a meeting, right? You're on a Zoom or a team call, and you're like, I just wrote this amazing benchmark. Woohoo! I could just sidetrack a little bit during the meeting and execute the benchmark there. Like, no, don't do that, because benchmarks require CPU and memory, are quite resource intensive, and Teams and Zoom is also quite resource intensive, right? That would skew the result. So make sure when you execute it, sort of hit the benchmark, run it, go grab a coffee, and when your boss sees you at the coffee machine, it's like, Daniel, you're here like the 10th time today and drinking coffee. What are you doing? It's like, well, boss, I'm optimizing the code. I'm getting the 20% performance improvements that you asked for, right? So do that explicitly when you're running the benchmarks. And I told you, delegate the heavy lifting to a framework, because essentially with benchmark.net, you get a library that is battle tested. The .NET performance engineers that are doing the .NET runtime performance improvements, they're also using benchmark.net to measure the things that they're doing. And this is a great library because it's sort of, benchmarking is really, really hard. I can tell you, even though I did a lot of benchmarks, I make countless mistakes, right? And if you have a framework that sort of makes sure that the most common mistakes that you will make, you're not going to make, that's pretty amazing, because it will sort of protect you from the common pitfalls. Like, for example, it will run your benchmarks in a dedicated process, so there is no static state, right? By default, it will also run several iterations until the result is stable. It will also, in the statistic analysis, it will also cut away outliers so that you have a result that you can trust, that probably what you're measuring is actually what you will be seeing also in your production code, right? I want to give you a sort of quick example, and I'm going to fly in the interest of time because the miking up took a little bit of a few minutes, and I want to make sure that we more or less end up in time, hopefully. I want to quickly show you an example in the interest of the trade-off. I told you benchmark should not be testing exception cases. With NServiceBus and the NServiceBus pipeline, I actually, even though I have this guideline, I made a trade-off. Because with NServiceBus, when a message fails in production with an exception, potentially multiple thousands of messages are sent back into the error queue. And that takes time, and it has to be as efficiently as possible. So what I'm telling you here is, even though we have guidelines, I've given you guidelines, you have your context for your code base to sometimes deviate from these guidelines and make your own decisions, and I did that as well. So I added a benchmark for the pipeline exception cases. So what I did here is I did another sort of benchmark, single responsibility principle, and configured the pipeline deepness, and I added to the bottom of the pipeline, I added a behavior that throws an exception, right? And then what I did is, that's here, add a behavior that throws an exception, and then I wrapped the sort of the execution of the pipeline within a try catch, and that's a benchmark that sort of verifies that also the exception cases are going well. Good. I'm going to skip over this in the interest of time. Then, once we have done that, once we have done the benchmarking, the improvements, we want to bring it back into the harness that we wrote at the beginning, because we want to see how the code actually looks like in the grand scheme of things. And that's what I've done. So I did the improvements, brought it back into the harness. And here I did another snapshot, because one of the good things that all these tools provide, whenever you're taking a memory or a CPU snapshot, you store it on disk. Right? So you can actually take the snapshot that you took in your first investigations, and then you do another run with your improvements, take another snapshot, and then you compare those. You can execute those side by side. And what we see here is, while previously we had 20 megabytes of behavior chain allocations, these are now gone on the other end. So we actually clearly optimized the code, and now other allocations are now visible. Then when we look at the receive side of things, what we can see here is that before we had sort of 653 megabytes of allocations, now we went down to 596 allocations, and the previous funk of behavior context of task allocations, they're all gone, and we see the effect of our performance improvements. Then when we look at sort of the stack trace, we saw it also on the flame graph. Previously, there was like lots and lots of infrastructure noise that we saw, and now we got rid of the infrastructure parts via our optimizations, and we can see how the stack trace also shrunk down, and how the memory allocations due to those optimizations are now clearly also better in the sort of the memory characteristics overview. And then we can filter into sort of the namespace that we optimized, and I did that. I filtered into the NServiceBus pipeline namespace, and what we can see here is that all the display class allocations, they're also now gone, and we can sort of tap ourselves on the shoulder because we actually made good improvements. And we can also do that by looking at the flame graphs, because when you look at the flame graphs, previously we had this lots and lots of red stuff, a little bit of orange, right? Sort of the production code, the actual business code was not clearly visible. And when we zoom in after the optimizations, we can now see that sort of the orange part starts lightening up in sort of the flame graphs as well, and the red stuff goes to the back. And when we put them side by side, it's even more clearly visible, just by looking at the sort of the flame graph, that we actually optimized the code. And so I can say that I basically removed 32.3% of the publish operations CPU stuff, and over 14% of the receive operations. They're all gone now by looking at this sort of flame graph profile, right? So again, I'm using the same tools that I used at the beginning to get an overview, to actually verify, once I've done those changes, back in the grand scheme of things, that we're actually improving stuff. But I told you that, well, I copy-pasted the code, and you might be already saying, if you're a little bit more advanced, yeah, but there is trade-offs when you do that, and that's totally true. I talked about those trade-offs. So sometimes when you want to make a step further in your sort of performance awareness in your team, you might want to take care of, what if someone changes the code that I optimized and introduces regressions? How do we prevent regressions from happening, right? Because the best way is to never have a regression at all, to already on CI/CD basically prevent these regressions from being there. So there is a thing in the .NET performance repository. There is a good guidance. I've linked it here on the slide. You will have this resource. It's called Preventing Regressions. And there is the result comparer tool. And what it allows you to do is, you can execute a benchmark with benchmark.net, and you can tell it to store the artifacts in one folder, right? So you execute it, and then what you do is, you essentially make the improvements, or you basically execute the benchmark on a git SHA here, and then here is your improvements. You execute the same benchmark again against the code changes, and you store the results in the after folder, right? Then you have both sort of artifacts of those runs, and then you execute the result compare tool, and you say, hey, I'm defining a threshold of a maximum of 2%. If the threshold of CPU or memory, you can further define that, is more than 2%, this tool will basically give you an exit code that sort of allows you to fail your CI/CD pipeline, right? So that's a good way to actually make sure the important benchmarks that you want to keep around, right? There might be some benchmarks that you're just going to throw away because they were just sort of a tool to achieve something, but some of the benchmarks that you want to keep around because it's a crucial infrastructure piece that you always want to test on CI/CD, that it doesn't regress, you can keep them in your source control, and then you can use this result compare tool and benchmark.net's storing of artifacts. But if you do that, you have to really take care of that your CI/CD environment is reliable. And Andrei Akinshin sort of wrote a good blog post about this. He tested GitHub action runners against CPU and memory and disk performance, and because it's a shared environment, there were consequences of that shared environment. And this is the result. CPU-bound benchmarks are much more stable than memory disk-bound benchmarks, but the average performance level still can be up to 3 times different across builds. So as you can see, is once you go on this path, on this journey of sort of putting stuff into your CI/CD system, you have to think about, well, maybe we cannot use our shared Azure DevOps runner or our shared GitHub action runners. Maybe we have to have dedicated resources in our cloud environments, maybe even custom prepare the OS images so that it's tweaked, so that our benchmarks that we execute on CI/CD are actually stable and we can trust the results, right? You can read this blog post in more detail in the resources. So I'm going to wrap up here this talk. So I showed you the performance loop today with examples with NServiceBus, which is a framework and library, but I'm 100% certain that I've done it in several business codes as well. The performance loop gives you a very structured approach to sort of go through this profile, improve, benchmark, and profile and ship the code cycles and the inner loop to make sure the performance improvements that you're doing actually make a measurable impact. And you can combine this sort of approach with profiling on sort of the macro level, right, to sort of see whether sort of the changes that you're making are actually are adding up over time to make your code faster. And I also want to give you away this. I always hear this from teams like, oh, this code is crap. Let's refactor this entire code because it's not even worth investing time into it. I'm going to tell you, I've seen this so many times. When you invest time into improving existing codes, you will significantly increase the understanding that you have of this code base, your team's understanding, and that cycling through these optimizations will give you, in your decision log, architecture trade-off log, whatever you're using, more knowledge to actually then, once you actually decide that you need to sort of really rip out this code, all the necessary knowledge to write new code that is going to be performed. Because if you're just looking at code and saying, this is way too complicated, let's replace the entire thing, I can guarantee you, you will make the same mistakes again, and it will not be fast, right? So use the knowledge from these iterative improvements to sort of improve the code base. All the stuff that I talked today about is on github.com/Marbach/beyond simple benchmarks. If you have more questions, I have business cards down there. You can send me also an email. I'm going to be at the particular software booth the entire day. I will also be at 1:40 at the JetBrains booth should you have any questions. And all the people that reach out to me over any sort of social media, email, or whatever, up to the end of tomorrow, I will raffle an entire .ultimate JetBrains license for 1 year. If you give me structured feedback about the things that you learned from this talk, what you liked, what you didn't like that much, so that I can improve this talk to make it even better. Thank you very much for listening, and have a good time.